All right, so we're going to take a look at section 6.5. Okay, sometimes I split it into two parts. We'll see how much of it we get through because I'm going to cut a few things out that we don't need in it. So we might be able to do section 6.5 in just one day. Right, we'll see what happens. All right, so this section is going to focus on right triangles. And basically the whole goal of this section is going to be, they'll give you a triangle and they'll ask you things about it. How long are the sides? How big are the angles? Okay. In order to do that, they have to give you some information to start. Anytime you want to solve a right triangle, you always have to be given three things. Well, one thing you'll be given is that it has a right angle, okay, which is a 90-degree angle. But in addition to that, you need two other things. And at least one of them has to be a side. Okay. So I'll always give you at least another side in addition to that. And then possibly either the third side, or I'll give you an angle. Okay, but I got to give you a certain amount of information if I want you to be able to solve it. All right, so any triangle with a 90-degree angle, that's a right triangle. And then the side across from the 90, what's the name of that side? Hypotenuse. Hypotenuse. And what's special about the hypotenuse compared to the other two sides?
It's the longest side.
Yep, it's always the longest side. And the other two sides, I was going to ask you that, but I just showed you. The shorter sides, those are called the legs. Okay, and what are the letters that we generally use to label the sides? You don't have to, but they generally use these three letters. Yeah, they usually use A, B, and C because that ties in with the letters that they usually use with a certain theorem. Okay, so we have a leg, which I've labeled A, another leg, which I've labeled B, and the hypotenuse, which I've labeled C. Okay, this Greek letter, theta, we've talked about the different Greek letters. This one is theta. Theta is just used to represent the angle. And I've said right here that this angle is always between 0 and 90. How come I know that? So is this one up here. But why? Because yeah.
All the angles in a triangle add up to 180, and if it's 90, then you can't have a triangle. It's not a triangle, you have to be a different shape. Or
Yeah.
if it's 0, then you can't add it up to 180 degrees. It's nothing.
Yeah. So in a right triangle, like Luke just said, or any triangle, all the angles have to add to 180. You've already used up 90 for the right angle, so the other two angles have to be between 0 and 90. Or it wouldn't add up to 180. Okay, and an angle between 0 and 90, that's called an acute angle. You would never have an obtuse angle in a right triangle. That's impossible. You can't have an obtuse angle in a right triangle. In a triangle like this, you can. But that's not a right triangle. Okay, so we'll talk about those kind of triangles, I think, in chapter 7. Okay, so the Pythagorean theorem, it's a theorem that we can use to help us specifically if we want to know the side lengths of a triangle. Sometimes I go through and show the proof of it. It's actually a very, very simple proof to do with just pictures. You don't even have to really write a lot down. You can just look at drawing a couple pictures and it makes sense. But today I don't think I'm going to go through it. But what is the Pythagorean theorem? Yeah?
A squared plus B squared equals C squared, so a leg squared plus the other leg squared equals the hypotenuse squared.
Exactly. If you use A, B, and C for your sides, which you don't have to, it's A squared plus B squared equals C squared, assuming A and B are the legs. So the general idea is exactly what Luke said. Leg squared plus leg squared equals hypotenuse squared.
Doesn't that actually have to do with like extending the sides out and like making squares with it, right?
Yep, you can make a square out of it, out of like 4 triangles.
Yeah.
Yep, you make a square out of it. I think there's tons of ways, dozens of ways to prove the Pythagorean theorem, but that's one of the easy ones, just drawing a square. Okay, so that's that. All right, now we're going to look at the 6 trig functions. Okay, but this time we're not going to look at them like we did on a unit circle. Okay, when we did unit circle, we had like sine was y, cosine was x, tangent is y over x. Well, what I'm about to show you here is actually the same thing. But we're not going to call things y and x. We're going to call them opposite, adjacent, and hypotenuse. Let's see. Does anybody already know any one of these three? They're all fractions, and they use something over something. And it's opposite, adjacent, and hypotenuse are the three terms. Anybody know, like, sine?
Sine over opposite.
Sine is opposite over hypotenuse, yeah. That's sine. Opposite over hypotenuse. How about cosine? Anybody know what cosine is?
Adjacent over hypotenuse.
Yep, cosine is adjacent over hypotenuse. And how about tangent? Tangent is opposite over adjacent. Okay, so the way you can remember that, because I was kind of writing on the board as we went. SOHCAHTOA, sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, tangent is opposite over adjacent. Okay, in past years, I had somebody say you could use Sacagawea to remember it. Yeah, she's not going to help you. SOHCAHTOA will help you, but not Sacagawea. So try to go with SOHCAHTOA. And now the other three. What do you do with each of the three on the left to get the three on the right? You flip them. So that means your cosecant is hypotenuse over opposite. Your secant is hypotenuse over adjacent. And your cotangent is adjacent over opposite. Now, one thing that's kind of important to understand are the terms opposite and adjacent. Okay? They're what we call relative terms. Okay? They're kind of like the words left and right. They change depending on which way you face. Right? So for me, left is the door and right is the window. For you, that's the opposite. Right? Left is the window and right is the door. So left and right change places depending on which way I face. So do opposite and adjacent. If you draw a right triangle, and let's say you mark where you're going to stand using that symbol right there. If you're standing here, opposite is the side that's furthest away. Adjacent is the side that's right next to you. That's not the hypotenuse. Okay, the hypotenuse is what we call, it's not a relative term, it's more of an absolute term. The hypotenuse is always across from the 90. It doesn't matter which way you face. Okay, going with my left and right analogy, that would be like up. It doesn't matter which way I turn. As long as I'm standing, up is the same for all of us. Okay? But left and right is not. It changes. Okay? If you draw your triangle, and instead you look at it from the perspective of this angle, okay? It's like you're standing in a different spot. Opposite is the side that's furthest away. Adjacent is the side that's next to you. That's not the hypotenuse. So, any questions on how opposite and adjacent can switch places? Depends on where they mark the angle. This is kind of like the reference point. Okay? Depends on where they put it. But they'll always tell you where it should go. Okay, does everybody have the 6 definitions? Okay. So next, I just want to look at these 2 triangles. Okay, what I've drawn here is 2 right triangles. And I've drawn the angles to be congruent. Okay, what that means is these triangles each have the same angles. 30, 60, 90. 30, 60, 90. So the angles are congruent, but that means the triangles are similar. Okay? One is, you could say it's an enlargement, or the other one you could say it's a reduction. It's however you want to look at it. Okay, but these 2 triangles are similar. So what I want to do now is, let's compare the sine of 30 degrees in the small triangle and the sine of 30 degrees in the big triangle and see what happens. Okay, so what's sine again? It's what over what? All right, so in the small triangle, what side, if this is, you're looking at it from this perspective, what side is opposite 30? 1. And the hypotenuse? 2. So the sine of 30 in the small triangle is a half. Now let's do it in the big triangle. What side is opposite 30 here? 2. And the hypotenuse? But what is 2 over 4? It's 1/2. So what I'm trying to show you is that it doesn't matter the size of your triangle. The sine of 30 is always the same answer, whether you have a big triangle or a small triangle. And that's true for any angle. And any trig function. The cosine of 30 would be the same in a small triangle or a big triangle. The tangent of 60 would be the same in a small triangle or a big triangle. The size of the triangle doesn't matter. Right? So any questions on that idea? All right, so next, we're going to look at a problem like this. Okay, I'm going to explain how to do it. They're going to tell us one of the 6 trig functions. In this problem, they're telling us that the sine of theta is 5/6. So we're going to take that information, and we're going to use it to label 2 sides of a triangle. Okay, because if we know the sine is 5 over 6, and we know sine is opposite over hypotenuse, we know the lengths of 2 of the sides. Okay, and it doesn't matter what trig function they give you. As long as they give you a fraction, or even if they don't, let's say they just gave you like a number like that, you could always make it a fraction. And we're going to label 2 sides. And then once we label 2 of the sides, we can use the Pythagorean theorem to get the 3rd side. And once you know all 3 sides in a triangle, you can find any trig function that they want you to find. But you have to know all 3 sides. Okay? And you have to be given a piece of information to start with. Okay? At least one piece of information. Okay, so that last sentence is just describing that now that you know all the sides, you can answer any question, any trig function question about that triangle. Okay, so these are really just the steps you need to know. But I just put a bracket around. Okay, any questions on the idea? We'll label 2 sides, use the Pythagorean theorem to get the 3rd one. Is that too small? Okay. So yeah, just copy what's up to there. All right, so let's look at example A. They said that we have an angle, and the sine of that angle is 5/6. Now the question here is not asking you to find the angle. Okay, could I find the angle with this information? Absolutely. I could tell you exactly how many degrees that angle is. But that's not what they want. They want us to just find all the trig functions. Okay, the sine, the cosine, tangent, the secant, the cosecant, and the cotangent. If we get fractions for anything, we'll just leave it. We won't round anything off to decimals. All right. So I'm just going to start by making a chart of everything I need to find. Cosecant, secant, cotangent. Okay, I'm also going to draw a picture. Now, you can put theta wherever you want. It doesn't matter if you put it at the top or you put it at the bottom. Okay, so your diagram might look a little different depending on where you put it, but all your answers are going to come out the same. I'm going to put it at the top. All right, so now what's the definition of sine again? It's what divided by what? Okay, opposite over hypotenuse. So in this triangle, how long is the opposite side? 5. And how long is the hypotenuse? 6. Now I'm going to use the Pythagorean theorem and get the third side. I'm just going to do it off to the side. You can call it whatever you want. You can call it x or a, just something you don't know right now. I'll call it a. So a squared plus what? 5 squared equals 6 squared. Oops, should be a plus sign. Okay, so we get 5 squared is 25, 6 squared is 36. So a squared equals how much? 11. So a is going to be square root of 11. Okay, and we're going to leave it just like that. The only problem we could run into is if we ever get a square root in the bottom of a fraction, we need to fix it. Okay, so now I know this is square root of 11. And what side is that in the triangle? That's the adjacent. Okay, so let's fill in all 6. Sine, we already know. Cosine, what's my cosine going to be? Square root 11 over 6. And what about my tangent?
It's going to be 5 over square root of 11, so you got to multiply it by square root.
Yeah, I'm going to multiply top and bottom by square root 11. And what would I get when I fix that?
5 square root of 11 over.
Perfect. So there's my sine, my cosine, my tangent. What about my cosecant?
Would it just be the sine from left, right?
Yep,
So it'd be
6 over 5. How about my secant?
6 square root of 11 over 11.
Yep, so you'd flip the cosine, but then when you flip it, that square root's going to go to the bottom and you need to fix it. And now for the cotangent, you have 2 choices. You could either flip the one I just circled in red or the one I circled in black. Yeah, why would you flip the first one?
Because you don't have to do any more steps.
Yeah, if you flip the first one, the root goes to the top and you're done. If you flip the second one, that's okay. It's just the root's going to go back to the bottom. You're going to have to fix it again, and you're just going to end up with the same answer. So notice we were able to describe 6 things about the angle, the 6 things that I circled in black, without actually knowing how big the angle is. We have no idea, is this a 12-degree angle, a 50-degree angle? We know it's acute, but we don't know anything else about it, and we don't need to. All right, let's find all the trig functions here. What trig function have they given me in this picture that I don't need anything else? I could actually do it just the way it is.
5, 9-degree angle, and then 12. Right?
So what trig function is that? Sine, cosine, or tangent?
That would be
That's tangent. We know the opposite. We know the adjacent. So if all they wanted was tangent, I can do that without any work at all. I actually could do one other one without really too much work. I could do the cotangent. And that would be 12 over 5. But now if they want any of the other 4, those 4 all have hypotenuse in it. So now I'd have to find that. Does anybody know what the hypotenuse is here?
7.
Well, it's got to be the biggest side.
Um,
So it's got to be bigger than 12.
15.
Nobody knows that one?
It's like always.
Mhm.
Okay, 13.
Yes, 13. It's a special right triangle. It's a Pythagorean triple. Okay, Pythagorean triple is a triangle where all the sides come out to integers, like 3, 4, 5. That's one a lot of people know. 5, 12, 13 is another one. There's infinitely many of them. Those are the two that I know, 5, 12, 13, and 3, 4, 5. Okay, so this time, square root of 169 comes out nice, so you have no square roots. So that's a little easier. So what is my sine? Ian? What's the definition of sine? No, sine is opposite over hypotenuse. Sine is opposite over hypotenuse. So what side is opposite here? So what does opposite mean when we explain that? So you don't need to know any trig functions to just figure out what's opposite and adjacent. Their position. Why is 5 opposite? Yeah. Right. It's the side that's farthest away from the angle. The 12 isn't going to have anything to do with this one. Okay? 12 is adjacent. So we don't need 12 at all. Okay. We will for cosine. So what would my sine be here?
Would be 5 over 13.
Yeah, just 5/13. And the cosine would be 12/13. Right? That's adjacent over hypotenuse. How about the secant? Nick?
13 over 12.
Good. Yeah, I said this one. I didn't say the top one. I was just seeing if anybody would say 13/5, but nope. Secant is 13/12. And how about cosecant? 13 over 5. Okay. So those are the 6 trig functions of that triangle. We still have no idea how big this angle is, but we know 6 things about the angle. And any one of these pieces of information is enough to find out the size of that angle. Any questions on that? So a couple special triangles we work with a lot are the 45, 45, 90. That's a special right triangle. And the 30, 60, 90. All right, so let's see if we can figure out the trig functions of those triangles. And eventually, those are good ones to memorize, like sine of 45, cosine 45, all that stuff, okay? Because they come up a lot. All right, what's the hypotenuse going to be in this case? It's going to be what? Yeah, it's the square root of 2. So let's go through. And now I'm giving you a specific angle to work with. Does it matter which 45-degree angle you stand at for your perspective? No, because the sides opposite both 45s are 1, so it doesn't matter which one you stand at. Now you might be like, well, how do you know both sides across from a 45-degree angle are 1? It doesn't matter what I make them. Remember we talked about this? I could make a bigger version of that triangle, and I could make them both 2 if I wanted. And it would change the hypotenuse, but do the trig functions change in larger or smaller triangles? No. So I picked the smallest triangle because I think 1s are easy numbers to work with. But if you don't want to use 1s, use any size you want. It'll come out the same. All right. So let's see, what's the sine of 45? About right?
45 over 45.
Well, we got to put in sides here, right?
1 over 1, or 1 over a half, or whatever that is. The square root of
Is one of those.
the second one,
Say that one again.
1 over square root 2.
Yes. Opposite over hypotenuse, which would be square root 2 over 2. Okay, how about the cosine of 45? About Connor, what's the cosine of 45?
1 over the square root of 2.
Yeah, it's the same thing. And it's the same thing because the opposite side and the adjacent side are the same thing. They're exactly the same length. Right? And how about my tangent? Oh, Jacob, what's my tangent going to be?
One over square root of 2.
So it's not over hypotenuse. What's the denominator for tangent? It's the, what side? Adjacent. Okay, tangent always has adjacent in the denominator. So opposite is 1, adjacent is 1. So the tangent is 1. So tangent of 45 comes out to a very nice number.
Why is the cosine square root of 2 over 2?
So cosine would be adjacent divided by hypotenuse. And adjacent is 1, and hypotenuse is square root 2. But you can't leave the square root in the bottom. So it comes out just like sine. But then we have to fix it. Okay? How about my, Alex, what about my cosecant?
It's gonna be square root of 2 over 1.
Yeah. You could put square root of 2 over 1, or you could just write square root of 2. While you're at it, how about the secant?
That'd be 2 over, actually, it won't be 2 over square root of 2. It'll be square root of 2 over 2.
Square root of, so you're saying the secant would be the same as that?
Yeah, because the square root of 2 can't be on the bottom.
Right. But if you flip that, it won't stay the same. It won't be square root of 2 over 2.
It'll be 2 over square root of 2.
2 over the square root of 2. All right, and then you said you got to fix that.
Yeah. Multiply by square root of 2. Right?
Just one quick thing. Do you notice anything here? Because you gave me this answer, and that's correct. And this one is the same as that one.
So it's just square root of 2?
So it's just square root of 2. If these two answers are the same when you flip them, they're still the same.
Oh.
Yep. So when you fix this, if you wanted to flip it, you could, but this is what you get when you fix it. 2 square root 2 over 2. And then the 2's cancel. There's only one number you can flip and it stays the same, and that's the number 1. So if you flip anything other than a 1, it stays the same. Or a negative 1 also, when you flip that, it stays the same. So that kind of answers the next question. What's the cotangent of 45? What is it?
Definitely not 1.
Then what would it be?
Joked.
I know. So, yeah, the cotangent of 45 is 1. Okay? If you ever get a negative 1 and you flip that, negative 1 also stays the same. But any other number, when you flip it, it has to change. Okay, so any questions on the 6 trig functions of 45? Okay. What's the other special triangle I said that we work with sometimes?
That's
Yeah, 30, 60, 90. This isn't quite a 30, 60, 90, but can somebody explain to me what's happening here and how I could make it into a 30, 60, 90? What's going on here?
And equalize.
It's an equilateral triangle, yep. So what does that mean?
All 60.
All sides are the same? What else? All angles are the same. So all the angles are 60, 60, and 60. That still isn't a 30, 60, 90 right triangle, though. I see a 60. But how could I turn this into a 30, 60, 90?
You take half of the two angles and then take half of the opposite sides.
You could change the lengths to 35 or whatever that one was.
Change the lengths?
Yeah.
Well, I could change the lengths, but that wouldn't change the angles. I could make them all 1, 1, and 1, but it would still be 60, 60, and 60.
Yeah, I know, just don't change them all to the same number.
Oh, but then it wouldn't be equilateral. I want to keep it equilateral.
Oh, and
So-
I have no idea.
If you change the,
Something I could add to the picture.
Another triangle, yeah.
Not another triangle, because I already have the triangle, but I want to add something. Yeah, just add, if you add a, whoops, just take and go like this.
wow, we were thinking.
Now from geometry, I'm not going to go through the reason why, but if you draw a line straight from one of the vertices perpendicular to the other side,
Cut that side in half.
it cuts the side in half, and it also cuts the angle in half. You could prove that these two triangles are congruent, okay? But what basically happens is that's a 90, and that's a 30. So off to the side, I'm going to sketch that. It was 90, 60, 30. Now, how long would this bottom side be? 1, because there's a theorem. If you draw that in, you cut the side in half, it bisects it. And this is still 2. But how would I get the third side? Yeah, just use the Pythagorean theorem. Call that a. So 1 squared plus a squared equals 2 squared. So a squared is going to equal 3. So what's a? Square root of 3. Now, you might say, well, why did I pick 2, 2, and 2 for the sides? You could pick 4, 4, and 4, 5, 5, and 5. You can do larger or smaller versions. It's not going to change the answers to the problem. I picked 2, 2, and 2 because I knew I was going to end up taking half of a side as I went through the problem with you. And half of 2 is a nice number that's easy to work with. That's why I picked 2, 2, and 2. All right. So now let's find the 6 trig functions of 30. What's the sine of 30? Oh, Curtis, tell me the sine of 30.
Sine of 30
Mhm.
is 1 over 2.
Sine of 30, yeah. Sorry, I was looking at something different. Yep, 1 over 2. How about, Adrian, what's the cosine of 30?
Oh, which one?
Cosine of 30. What's your definition for cosine?
1 over square root of 3.
That's going to be your tangent.
Oh,
What's the definition for cosine? It's
it's opposite over tangent. I mean, opposite over hypotenuse.
opposite over, yeah, for cosine, it's adjacent over hypotenuse. So what side is adjacent to 30?
That'd be square root, so square root of 3 over 2.
Yes. And the tangent, that one you just said, that's opposite over adjacent, which is 1 over the square root of 3. And then we fix it. Okay, John, how about my cosecant?
That's going to be 2 over 1.
About Bria, my Secant?
It would be 2 square roots of 3 over 3.
Perfect. 2 square roots of 3 over 3. And my tangent would be, cotangent would be square root 3. Now, it said to find the 6 trig functions of 30 and 60. What's going to happen in this triangle if you go from standing here to now standing here? What happens? What's going to change? Yeah, yeah.
Tangent flips and cosine and sine switch.
Why? What's causing that to happen?
The corner of the angle is in these switch, causing the alternate to become the adjacent, to become the opposite, and the hypotenuse stays the hypotenuse.
Yes, the opposite and the adjacent are going to switch places if you switch where you're standing. So you're going to get all the same answers again. They're just going to be in different spots. Okay? All these 6 answers are going to move around. So if we did the sine of 60, sine is opposite over hypotenuse. So that's square root 3 over 2. Cosine is, remember, it's from the perspective of this angle now. Okay? Cosine is adjacent over hypotenuse. So that's 1/2. And tangent of 60, that's opposite over adjacent, square root 3. And now to get the other 3, just flip them. Okay? And then we'll look at them and kind of compare. But I think Ian already really described what kind of switch places. So that's going to be 2 square root 3 over 3. The next one is going to be 2. And the cotangent is square root 3 over 3. So between the 30 and the 60, which ones switch places? Hannah, do you see it, one that switched places?
It would be
The cosine and which other trig function switched? Cosine and anybody help her out? Nick?
Sine.
Yeah. These 2 switched places. Notice the sine of 30 is the same as the cosine of 60. And the sine of 60 is the same as the cosine of 30. Which other 2 switch places? Yeah.
Secant and cosecant.
Yep. These 2 switch places with these 2. And the last 2 to switch places were the tangent and the cotangent. Those 2 switched. And if you look at it, what switched places, it kind of makes sense. Just look at the words. Sine switched with cosine. Secant switched with cosecant. And tangent switched with cotangent. So each function flipped with its, what we call its co-function. The co-functions switch places. Okay. Now that only happens when this angle and this angle add up to a certain number. Okay. You could probably guess in this case, it's when they add to 90. Okay. If you have angles that add to 90, that pattern always happens. All right, I think we already answered this question, kind of. 2 acute angles in a triangle, or 2 acute angles in general are complementary if they add to 90. Okay, that's what complementary means, they add to 90. And I'm saying that these two angles right here are always going to be complementary. Why do those two that I circled in blue always have to be complementary? Why do they have to add to 90? Yep.
Because you have one angle that's already 90 and all the angles have to add up to 180, so that means you have 90 left over.
Yeah, exactly. Did everybody? Yeah. All right. So that's the answer why. When we label angles and sides, I'm going to do it a little differently than the book. Okay, I'm going to label sides using English letters, okay, A, B, and C. But the book does something a little different for angles. They decide to still use English letters, they just use capital versions. We're going to use Greek letters. Does anybody know why I might want to stay away from using a lowercase version of a letter and a capital version of a letter?
Confusion.
Yeah, it could be confusing, first of all, because if you ask me, well, what is C? And we're doing it the way the book says, I'd have to say, well, do you mean capital C or small c? And then if you're writing an answer on a test and you put a C, and I have nothing else in context to look at that, I can't tell if that's a capital C or a small c. So we're just going to avoid that confusion. And this is how you'll always label your triangles. Use A, B, and C for the sides. A and B have to be the legs. I don't care where you put A and B. And this Greek letter, does anybody know this one? Looks like a fish, yes it does.
Nailed it.
Does anybody know what they actually call it though?
Fish,
First Greek letter in the alphabet?
Alpha.
Alpha. And how about the one at the top?
Beta.
That's beta. However you draw your triangle, okay? I don't care if you want to draw your 90-degree angle like this. That's perfectly fine. That side always has to be C. That has to be A and D. Always put alpha across from A. Always put beta across from B. A is across from alpha. B is across from beta. C is always across from the 90. It's always the hypotenuse. Okay, so draw your triangle any way you want. Just maintain that relationship I just said. A across from alpha, B opposite beta. As long as you do that, however you draw your triangle, you'll always get the right answer. And that we're not going to do. Okay, so any questions on that? Okay, so it's a good diagram to have for any right triangle problem you need to solve. All right, so we'll start this, but I don't think we're going to finish that. So if they ask you to solve a triangle, what that means they want you to do is find out how big are all the sides and how big are all the angles. So there's 6 things, 3 sides, 3 angles. But I have to give you some information to start. I can't just say solve the triangle and not give you enough information. So I will either give you one of these 2 scenarios. In addition to the 90, okay, that you're always going to have that. I'm going to give you either another angle in one of the sides, so there's 3 pieces of information, or in addition to the 90, I'll give you 2 other sides. Either way, you're always going to have 3 pieces of information. I will never give you 2 angles. That wouldn't work. Okay, I have to always give you a side, otherwise you have no scale for the size of the triangle. Like if I just said, here's 3 angles, 60, 60, 60. How big are the sides? You don't know. Okay? So I always have to give you at least 1 side. Sometimes I'll give you 2. When you're solving a triangle, make sure you keep in mind the Pythagorean theorem. That can help you find the sides. And keep in mind that all the angles in a triangle have to add up to 180 degrees. Okay, so those are really the only, other than sine, cosine, and tangent, knowing those, and these two tracks, that's all you need to solve triangles. Also, when we're solving a triangle, we will not use secant, cosecant, or cotangent. Main reason why? We don't have buttons for them on the calculator. We're going to stick with sine, cosine, and tangent because they can do everything we need. Okay, so when you're solving a triangle, you can kind of forget about secant, cosecant, and cotangent. That's what I just said. So how do you decide which one of the three you should pick? Well, it depends on what you know and what you want to know. Okay. So they'll give you something in the problem, that's what you know, and then you're going to want to find something. Depending on what you want to find, you'll either pick one of those three. Okay. It's easier if I just draw a diagram and show you. So they're telling me that I have a right triangle. One of the angles is 37 degrees and the hypotenuse is 8. Doesn't matter where you put the 37. And my drawings are never to scale. So I'm going to go like that. I'm going to call this side A, B, and that would be C, but we know it. And then, if this is A, what angle is always across from A? This would be alpha, but we already know it. And what angle is already across from B?
Beta.
Beta. So what I do when I have to solve a triangle is I just make a chart of everything I have to find. You don't really have to worry about this because this is always given. That's the right angle. It's always 90. Okay. Do I know A? No. Do I know B? No. Do I know C? Yep. So I don't have to find that. Do I know alpha? Yes, because alpha is the one that's across from A. Now, was I given beta? No, I wasn't given beta, but I can easily find it by doing what?
Adding 90 and 37.
Yeah, just subtract, you really can just take 90 minus 37. Okay. Beta has to be 53 degrees or these angles wouldn't add up to 180. Okay, so that's one of the three things we need to find. So we've got beta. Now, whenever I want to find sides, I have to pick an angle. Technically, I have two choices. I could pick the 37, and I could work with that, or I could pick the 53. Which angle do you think is better to work with? Why the 37? Yeah, it was given. Try to stay away from something you calculated, because if you calculated it wrong, then other stuff comes out wrong. So let's use the 37. And we're going to use the side I was given. And let's pick either A or B. Let's do A. What's the name of this side since it's farthest away? It's opposite. What's the name of this side since it's across from the 90? Hypotenuse. So now we can answer that question. We know the hypotenuse. We want the opposite. There's only one trig function that has those two. Sine. Okay. So because we're using opposite and hypotenuse, that's sine. And what's the angle I'm using? So the side of 37. What's opposite the 37? A. And what's the hypotenuse? 8. Now how would you move the 8 to the other side and get A by itself? Multiply by 8. And that's the answer for A. Okay, you have to type that in. Okay, just make sure your calculator is in degrees. And type it in exactly the way you see it. 8 sine 37. Okay, So A is about 4.81. Now, because you have A and you have C, you could use the Pythagorean theorem to find B. But why do you think I would probably avoid that? Right. If you made a mistake with A and you use it to find B, now B's wrong. Okay, the way I would find B, go back to the angle you were given, go back to the side you were given, and find B. What's the name of B? We didn't label it. So now we want the adjacent. We have the hypotenuse. What trig function has adjacent over hypotenuse in it? Cosine. So you basically do the same thing again, except use cosine instead of sine. And that would give you B. If you get B that way and you have extra time, you can check if a squared plus b squared equals c squared, roughly, okay, because you rounded this off, so it might not be exact. Okay, but I would not use the Pythagorean theorem here because you weren't given A. Okay, so any questions on that? And we'll practice more solving triangles tomorrow. All right, so the homework for tonight. Okay, we can definitely do 1 through 14. 21, 22 is okay. All right, I'm going to have you skip for tonight 25 to 32. Write it down. It'll be part of tomorrow. Okay, skip that. You can, and here, I just want you to do 41. And you can skip 51 for tonight. Okay, so skip 25 to 32, skip 51, and don't do 40 to 43. Just do 41.